Hiya. So in this video, we're going to look at an example of how to calculate eigenvalues, eigenvectors, and all that jazz. So let's start off by denoting that this is an example. And we're going to start off with some basis B. That's an orthonormal basis from some three-dimensional Euclidean vector space. And we're going to consider the linear operator P that's defined by the following things. So here's the linear operator. And we're going to have the conditions that, notice how here EX goes to EY and EY goes to EX. So these two just swap X and Y. So that swaps the first two basis vectors. And then this one just inverts, right? So it just goes minus. So inverts the third one. So this is what we're going to be using in our example. So I'll rewrite these on the side here. So we kind of keep track of them. EX is equal to EY. EY is equal to EX. And EZ is equal to minus EZ. Okay. So first thing what we were going to do is we're going to find what the matrix is. So the matrix for this is given by, again, everything's column vectors. So the first EX gives me an entry in EY and 0 everywhere else. So that's 0, 1, 0, right? So this is coming from EX. Then we have EY and EZ. So 1, 0, 0 for EY. And EZ just takes the inverse. So we get minus 1. Now we're going to be told that the eigenvalue is equal to lambda. So here I'm not having you calculate it. We're going to just be told that lambda is equal to 1. And I'm saying find its associate eigenvectors, plural, eigenvectors. So in essence, what I'm asking you to do is find that space, that one-dimensional line of all the possible eigenvectors given one of them. So let's see what this would do. So an eigenvector, right? This is just some vector. So we're going to write it as a vector. So here we're going to take some vector, right? This is some vector. This is arbitrary. I'm not saying this is the vector. I'm saying this is potentially one of them. And we're trying to figure out when is this an eigenvector, right? We're trying to solve this. So I have the property, right? So I have P of X is equal to lambda of X, right? This is definition eigen, right? And we also have that lambda is equal to 1. So we can kind of just get rid of the lambda and not have to worry about it. Now here I can take this X and move it to the other side. So I can take this X and move it to the other side. And that'll give me P of X minus X is equal to 0. And then what I can do is I can convert these into matrices. So what does this look like for matrices? This gives me the P matrix of B given some basis B minus the identity of X associated to B. And this has to be equal to 0, the 0 vector. Yeah. And then at this point, it's basically just putting things in. So here I have P minus I. So P minus I3 is here. And then this is X of B. Right, so here I have the minus 1, minus 1, minus 2, because minus 1 is minus 2. And then this is going to, we want this to equal to 0, right? So we have this equation. So if we solve these, right? So we solve these. So minus 1, 0 with x, y, z. This gives me minus x plus y is equal to 0. The next line gives me x minus y is equal to 0. And the final line gives me that minus 2z is equal to 0. If we look at these, we basically have that x is equal to y, right? So this is the first condition, that x is equal to y. And the second condition is basically saying that z has to be equal to 0, right? And so using these equations, this gives us precisely our eigenvector. In other words, eigenvectors. So in other words, we basically have x, so the eigenvector x is just alpha, some number, we don't care which one, such that e of x, that alpha times e of x plus e of y, right? Because e of x and such that because x and y have to be the same, right? X and y have to be the same. This implies that we have alpha ex plus alpha ey, right? They have to be the same. And the z component is telling me that we have plus 0az, right? And this is precisely our x, right? This is what we were trying to solve. And so that gives us the all of the different eigenvectors that are associated to the eigenvalue 1. So nice and easy, nice and cool. So yeah, so we'll stop this video here, and in the next video we'll talk about orthogonal linear operators. So what happens if we now restrict our linear operators to being orthogonal? So I will see you then. Peace.